Hello everyone, welcome back to yet another video in segmentary series. If you are new, this is a new series that we have started in which we are trying to dissect segmentaries from scratch. In the previous videos, we have discussed about the basis of segmentary. We started from all the way up to what segmentary is, how to build segmentaries, how to do point updates, range queries. We discussed the complexity analysis and the involved proof behind each of these methods and the entire code walkthrough. And then we solved couple of varieties of different problems of various difficulty on queries on prefix of the array. We looked at how segmentary structure grows very similar to how binary search works, and we looked at how to do binary search on segmentaries as well. And finally, in the last couple of videos, we have looked at what is merge sort and solve some problems on merge sort trees as well. So there is a Google sheet bit.ly/segmentaries in which we have maintained all the videos, the related practice problems for you to understand and solve similar problems about segmentaries. If you go through the sheet, I am very sure you will be able to strengthen your understanding about segmentaries. Starting from this video, we will be starting our journey from of persistent segmentaries. So next couple of videos will be about persistent segmentaries, and this video will be an introduction to this data structure. So with that, let's get started. Just like with any other data structure, we should actually understand what this data structure solves or why it exists in the first place. So let's start with that. So let's start with a simple problem. Let's say you are given an array and some queries. Queries are similar. Queries are simple. You have updates and a query. Update is update the ith element to the value x, and queries are L comma R, which says give me the sum of everything between L and R, right? So this problem can very well be solved using usual segmentaries. You can just build a segmentary on this array. Updates will be just order login operation, and queries also you can do in order login time. Now comes the interesting part. Let's say the queries are modified a bit. So instead of queries like this, you are also given a time at which this query arrives. So basically this update arrives at t equals to 0, this query arrives at t equals to 1, and so on and so forth. And with each query, along with L and R, you are also given some t dash. This denotes the time at which you need to answer this query, right? So in this case, t dash is 0. It means you have to answer the query at the time t equals to 0. In other words, at t equals to 0, the state of the segmentary was this, state of the array was this. So you have to find the sum between 1 and 3, which is these 3 elements, at t equals to 0. So the sum would be 4 plus 5 plus 1, which is 10. So the sum would be 10 here. Similarly, let's say again an update come at t equals to 2, which says update the 5th position to 9. But then a query comes which says I want to query at time t equals to 1. So even though we have updated the 5th element, we will not consider this update at all while answering the query, because it asks to return the answer at t equals to 1, right? So this problem can this problem can be solved using normal segmentary as well. I would encourage you to think about the solution, but this is one of those areas where persistent segmentary would beautifully solve this problem. So what you can say is, okay, if you see any update here can change the segmentary. For example, if you update the second element to 5th, if I update it to 5, this will change this to 6, and this will be changed to 11, and finally this will be changed to 20, right? Now once you change the segmentary, you can't actually answer the query at t equals to, let's say, -1. You can't do that, right? Because you have changed the query, to change the segment tree itself. So if you want to answer that query, you need to store the segment tree at different timestamps. So in this particular scenario, let's say we build 3 segment trees. First segment tree was at t equals to 0, and then at t equals to 1 there is an update come, so we build a segment tree at t equals to 1. Then at t equals to 3 another update comes, so we build another segment tree at t equals to 3, right? Now whenever a query comes, we will just look at what is the nearest segment tree which can answer the query. For example, in this case a query comes for t equals to 1, so we will look at what is the nearest segment tree at t equals to 1, and we found this is the nearest segment tree which represent the state at t equals to 1. We will just look at this route and query the given range L2R. Similarly, when you have to query this particular segment tree, you will look at what is the nearest state of 2. Again, it is 1 itself. You will again go to this route and query the given range L2R, right? So if you maintain these multiple segment trees, again, how to maintain multiple segment trees is something a different question altogether. But if you have multiple segment trees, you will be able to answer these kind of queries very efficiently without any issues, right? So basically we are persisting older state and not destroying older state. So this was the older state, we are not destroying this, instead persisting it and creating a new state altogether. And similarly we will persist t equals to 1 and create something new altogether. So because of this persistent, this data structure is called persistent segment tree. So the idea is this simple, you just store whatever you had before, right? Now you might be thinking, okay, is this persistent segment tree only helpful when there is a notion of time? In this particular example we had a notion of time, basically each query was at particular time. But is the persistent segment tree only useful in these scenarios? The answer is no. It is helpful, or you can model a simple array and use persistent segment tree there as well. How? Let's say a few videos back, while we are discussing merge sort tree, we discussed one problem, which is this part 10 of the video, in which we discussed how to query the number of element less than equals to k in the range L2R, right? So to solve this problem we used merge sort tree, but this exact problem can be solved using persistent segment tree as well. Notice here there is no notion of time at all. So how to solve this using persistent segment tree? Let's just look at one solution. So the solution is very similar to how we have found out the number of elements less than equals to k in the range 0 to r using normal segment tree. So a few videos back, during the starting of the series, we had one video where we have discussed how to find out the number of smaller elements in the range 0 to r or 0 to I that is less than equals to k. We solved for the current element, number of smallest element less than equals to 1 or 6, but we saw that it can be done for any k as well. So in that video we solved how to figure out the number of smaller element less than equals to k in the range 0 to r. So you can just extend that idea and solve and use persistent segment tree to query in the range L to r. How? Let's look at it. I will just give a brief intro of what the solution was. If you want a deep understanding of what the solution is and how actually we derive the solution, I would encourage you to go through this video. I will link that in the description down below somewhere. So let's say this is the array, and we want to find out the number of element less than equals to k in the range L to r. So for now we are looking at number of element less than equals to k in the range 0 to r. So if you look at, let's say this is r, you want to query the number of element less than equals to k in this particular range, right? So what we have done, we initially sorted the array. Again, why we sorted the array and the actual logic behind it, you should refer that video. But we first sorted the array. So 14212 was the array. We just sorted it, and this was the sorted array. Now what we said is each of these element is inactive. As and when we will go through the array, we will activate the elements, and then we will be able to answer this query very efficiently. So let's look at one example. Let's say we want to query the number of elements less than equals to 1 in the range 0 to 0, or basically r is 0. So in this case, you will simply say, okay, how many elements are there which are less than equals to 1, and you will simply count the number of element. You will simply sum all the elements here. So currently everything is 0, so you will get 0. So basically you will say number of elements less than equals to 1 is 0, right? So before you move to 4, you will activate 1, because you have now seen 1 as well. In other words, for whatever calculation you will do afterwards, 1 will be there in that, or one can be contributed in that computation. So you will just activate this one. Now you saw 4, so you want number of element less than equals to 4 in the left, or in the range 0 to r. So again, these are the elements which are less than equals to 4. Why? Because the array was sorted, right? So you will just simply say these are the elements which are less than equals to 4, and we know for sure that only the element which are in the range 0 to r is activated, others are not activated. So you will simply find the sum in this range, and you will get 1. So there is just one element which is less than equals to 4 in this range 0 to r. And similarly, let's say r is this. So again, before going there, you will activate 4 as well. So you will just activate the 4 so that it is contributed, or it is counted for the future queries. Now for this r, again you will say how many elements are there which are less than equals to 2. How to do that? Again, these all are the elements which are less than equals to 2, and we know that only the elements which are on the left, or which is in the range 0 to r, is activated. So you will just do a range sum and you will get the value, right? So hope you got the intuition how we are solving this. So currently we are finding out how many elements are there which are less than equals to the current element, but you can see it can be extended to any k. So current element can be anything, so it can be extended to any k very easily, right? You just need to do, let's say k is 3, so in that case you just need to do what is the range sum in this particular range, and that should be it, right? So basically we are able to find out how many elements are there which are less than equals to k in the range 0 to r, right? And if you think about it, you are able to find out how many elements are there in the range 0 to l minus 1 as well, right? And you can just subtract these two to get the final result, that how many elements are there which are less than equals to k in the range l to r. Now once you query for 0 to r, right, you will not have what you had when for 0 to l minus 1, right? So you can store, or you can pre-compute and store the values at l minus 1 as well, but let's say all the queries are dynamic, you are not given all the queries at once. So in that case, you don't know what l would be, so you can't actually store the result of every indexes from beforehand, right? So in that case, you need to dynamically query. So to query this thing, number of elements less than equals to k in the range 0 to l minus 1, you need the array which was at the state when we have only considered l minus 1 elements, right? So that thing is something you can store and persist using persistent segment tree. So let's take one small example. Let's say you need to find the number of elements less than equals to 3, so k is 3 in the range, let's say 2 to 5, right? So if you need to do this, you need to understand first what is the state when only 0 and 1 was included, and then you need to know the state when everything up till 0 to 0, 1, 2, 3, 4, 5, when everything up till 0 to 5 was included, and you just subtract these two to get the answer. So when only 1 was included, this was the state. When 4 was included, or in other words, when 0 and 1 both elements are included, then this was the state, only 4 and 1 was activated, right? And similarly when 0 1 2 or everything up to 2 is activated, then this was the state. Basically we have activated these three elements only, right? And in the same fashion we have every other state stored. Now when you have to compute everything in between 2 and 5, you will just go to the state at I equals to 1, right? Figure out how many elements are there which are less than equals to 3. So for that you will just do a range sum in this range, right? So you know that there is one element which is less than equals to 3 in the range 0 to l minus 1, and in the same fashion you will just do 0 1 2 3 4 5. So this is 5, so you will just do a range sum in this range again to get how many elements are there which are less than equals to 3 in the range 0 to r. So there are like 4 elements which are less than equals to 3 in the range 0 to r. You can subtract these two and finally get the result for how many elements are there which are less than equals to 3 in the range L to R, right? So this all arrays is something you will create segment trees on. So basically you will have one segment tree on this array, 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 and so on and so forth. And whenever you need to answer for the range L to R, you will look at two segment tree: the segment tree of rth index, or the segment tree which contain everything from 0 to r, and the segment tree that contains l minus 1th index, or the segment tree which contain everything from 0 to l minus 1, and just do the query in those two segment tree and subtract the result to get the answer, right? So here we saw that there is no notion of time at all, but we considered the indexes as time itself. So as and when array elements are coming, we are saying that okay, our array is incrementing with time, right? So we just considered that as time axis, and we build multiple segment trees, and for any query we now have to query two different segment trees to get the result. So we looked at what a persistent segment tree can give us. It basically can help us query the array or query the state at a particular time. Now time may not be an actual time, it can be a virtual time which you have created based on the problem statement. So in this case we have created time axis on the indexes. So as and when indexes are increasing, we are saying that there is some change in the array with respect to time. So we saw that persistent segment tree requires building multiple segment trees. Here also we saw that we require to build 3 segment trees. Here also we saw that we are required to build n number of segment trees. So the next question that we should try to answer is how to build persistent segment tree itself. So let's continue with this example, right? And if you look at this, if you try to build segment trees after each update, let's say after the first update the first element was updated to 3. So if you try to build a segment tree for this array independently, you will require order n time, right? So in worst case, to build, you will be building q number of segment trees. Basically for each query you are building a segment tree. So in worst case you will require q into n number of space or n space, and the same complexity as well, somewhere around same complexity as well. So this is surely not efficient, because we usually know that q is of the order of millions, or 1/10 of million, and n is also of the same order. So this will surely not pass the usual time constraint. So we need to do fast. Now how we will do better is the question. So notice that when you are updating, so we are updating the first element to 3, right? So whenever you are updating, what all things will change in the segment trees? We know that update takes order log n time. Why it takes order log n time? Because it only updates log n number of nodes, right? So we know that only log n number of nodes will change. So let's take an example. Let's say you are updating the first element to 3. So you are updating this to 3, right? So this piece will be changed to 3, right? So there will be or let's say this will be changed, this will be changed, this will be changed, and this will be changed. These are all the nodes which will be affected, but rest other node will stay as it is, right? So you can see only login nodes are affected, rest all the nodes can be shared across the new tree and the old tree. And that's basically the idea of how we can uh, build this persistent segment trees efficiently. So in this particular case, we know that all these nodes will be changed. So let's just create a replica of these nodes, right? So we have a replica of these 4 nodes with us, right? Now what will you do? You know that this will be changed to 3, so you just added a 3, right? And now you know this will be changed, so this, what will be the value for this? The value for this would be the left child plus right child. Now what will be the left child of this? Notice that you haven't changed or you haven't touched the left part at all. So whatever was the left child of original node will be the left child of this node as well, right? And what will be the right child? Right child will be the new node that you have created. So left plus right, which is 4, so this will be 4, right? Now the same technique here. What is the left child for this node? You have modified it, so this is the new node. What is the right child? Right child would stay as it is because you haven't touched it. So whatever was the right child of the previous node at this level, that same node will be the right child of this node as well. So what is the sum? Sum is 7, 4 plus 3, so this will be 7, right? And finally for this one, again the left child will be this and the right child would stay as it is because you haven't touched that at all. So the sum here would be 16, so this will be 16. Now you see, if you look at these this blue nodes or this the segment tree with blue root, let's say this is a segment tree with this root, just forget about these nodes completely, right? If you look at this, this is a complete new segment tree, and this segment tree denotes the exact segment tree which you have built, which you would have built if you start from scratch with this array or with this updated array, right? And what is the time and space required to build this new segment tree on top of the original tree? It is just log n, because you created log n number of nodes and you computed log n number of values. So to create a updated segment tree, you just require log n extra space and log n time as well, right? And in the same fashion you will do all other updates as well, and hence every update that you will do will create a new root node and the root and the nodes which are updated, and only log n number of nodes will be updated. So every update you will be able to create one new segment tree with just log n time and space complexity. So let's just take one more example to clarify it a bit further. Let's say you want to update the 5th position to 9. So 0, 1, 2, 3, 4, 5. So 5th position is now 9. You want to do this. Now notice that this 5th position to 9 is an update on top of this array, like on top of the array which was there after updating the first position to 3, right? So basically whatever new you will build, that should contain 3. In other words, whatever you are building should be on top of this blue tree itself. It will not be on top of the red tree, right? So let's just change the color, and let's say you want to update the 5th one to 9. So this is 5th position, so you will just create a new node, right? You will create a new node here because you know this will be changed. Similarly, you will create one new node for this because this will be changed, and finally root node will be the new for sure, right? So think about it again. This will be changed to 5, or sorry, this will be changed to 9, right? Now what will be the value of this? Sum of left and right child. So the sum of left child would stay as it is. Now what will be the left child? Left child would be the left child of this blue node at this position. So blue node at this position is equivalent to the red node at this position. So left child of that node will be the left child of this one as well, and right child would be the new node. So 2 plus 9, 11 is the value here, and in the same way the left child of this node would be this, and the right child of this node would be this. So the value would be 11 plus 4, 15. And finally, for this node, the left child would be the left child of the root, which is 16. So left child of 16 is 7, right? So this will point to this node, not 8. Okay, and the right child would be 15 itself. So the value would be 7 plus 15, which is 22, right? So you see how neatly you are able to build one more segment tree on top of this. So now forget about these nodes completely, right? And if you look at whatever remains, or also these nodes, so sorry, not this one, this one. So whatever remains is the black segment tree, or is the segment tree which will be representing this particular array 1 3 2 1 2 9 0 4, right? So again we will just update login number of nodes and change the login we change the values at this login nodes itself. So each update takes login time. In other words, we are able to build one new segment tree on top of previous segment tree in just login time, and hence we are able to build all the n segment trees in just login time each. So overall complexity to build entire segment tree, and let's say you have to build one segment tree for each of these scenarios, you will build a segment tree for this just like usual, and then you will keep on updating that segment tree one by one, right? So you will create a new segment tree based on this segment tree and only update this value, so it will take login time. Now whatever segment tree you will get, you will update this value to 1 and create a new segment tree on top of it, and so on and so forth. So to maintain this n number of segment tree, you will require login time each to build this, and login space complexity as well. So total space that you will be requiring is n login to maintain this n segment trees, and the time complexity will also be same, right? So this is how it will look like. It is exactly similar to the structure that we have just looked at before, just a bit more neat. Now let's try to answer some queries. So let's say you want to query this 1 comma 3 at 1. So what you will do, you will figure out what is the segment tree at 1. So segment tree at 1, you will say okay, segment tree at 1 is the one which have red which is of a black node. So you will just go to the segment tree and then query the range 1 2 3. How you will query? The usual segment tree structure itself. So let's just try one example here. Let's say we try to query 1 comma 3. So this is 0 comma 7. 0 comma 7 doesn't completely overlap with 1 comma 3, right? So you will go to both left and right. So you go to the left as well as to right. Now if you go to the left, you hit here, which is 0 comma 3. Again 0 comma 3 is not completely overlapping with 1 comma 3, so you will again go left and right. So again left of this would be this and right of this would be this, right? Now when you go here, 0 comma 1 is completely outside of 1 comma 0 comma 1 is not outside, so again this is not completely overlapping, you will go both left and right? And finally you reached here, which is 0 comma 0. 0 comma 0 is completely outside of this range, so you will simply return 0 from here, or any value which will neutralize everything. So in this case we want to find the sum, so we'll just return 0 because 0 plus sum x is equals to x, right? So we just return 0, a neutralizer value, and we reach 1 comma 1. 1 comma 1 completely overlaps with this, so we just return 3 from here. Notice that we are iterating over the black trees or following the black arrows. We are not touching the red arrows anymore. So even though the red one points to 4, we will be touching the black one, which is returning 3 here. And finally you will return 0 plus 3, which is 3 from here, right? And now you go to the right. Right is this part itself. This is completely overlapping with this, so you will simply return 3 from here, right? And finally 3 plus 3 is 6, you will return 6 from here. And if you look at the black one, this will be 4 comma 7, which is completely outside of this range, so you will return 0 from here. So finally 6 plus 0, you will return 6 from here. So basically after this update, the value would be 6, and you can see it is indeed 6 because this value will be staying as it is. This will be updated to 3. This will be staying as it is. This will be staying as it is. So if you look at, if you sum these three things, you will be getting 6, right? So hope you got the idea of what persistent segment tree is and how we can build it efficiently. Now let's just look at how to implement this data structure effectively. So notice when we were talking about implementing the usual segment trees, we have taken the approach of an array. In other words, we have said that okay, at the 0th, this is the ith, if this is the ith index, this will be the 2i plus 1th index of the array, and similarly this will be 2i plus 2th element of the array, right? So we started with 0, this is the root node, 2i plus 1, which is 1, so this is the left child, 2i plus 2, which is 2, this is the right child. So basically whatever the value here, we will store at this particular index, and so on and so forth. But now it will no longer be true, because if you look at it, the indexes, this point or this node will be pointing to something which will not be which is not easy to maintain at this structure, right? So every time the left child will not be 2i plus 1. So we can still use array and avoid pointers. If you remember, we avoided pointers. Rather than it is tree, we still avoided pointers by saying that pointers are difficult to handle, right? But if you are looking at the persistent segment tree for the first time, I would encourage you to implement it using pointer. I myself have started coding persistent segment tree for the first time, or at least for the first few months, with pointers only. Even now, I found pointer approach to be a bit easy, to be frank. So what we will do, instead of now storing segment trees as a array, we will now store segment tree as actual trees. So what actual trees it is, every node is an actual node where it will contain a value and a pointer to the left child and a pointer to the right child. So these are the three things it will be containing, right? So now these are actual pointers which are stored in the root node itself. And similarly at this node you will be storing 8, so the value of val would be 8. The left pointer will be pointing to this node and the right pointer will be pointing to this node, right? So this is how you will be building the initial segment tree, right? So once you build the initial segment tree, now is the time you will do updates. So whenever you do update, you will look at the previous segment tree node or previous root node and update the current node based on that. So this is how the pseudocode would look like. We will keep, or we will build the current segment tree based on the previous segment tree. So we have a previous root, and then we have an LLR which denotes the current range, and then we have an index and val. Basically we are doing point updates, we are updating the value of this index to this particular value, right? Now if you remember, previously we had L, R and I, where I denotes what is the index which we are looking at. In other words, this I was a pointer to the current node. But now, as we mentioned, we are maintaining the structure as an actual tree node itself. So we have to maintain a actual tree pointer with us. So we maintain the previous the pointer which denotes the range L and R with this particular prev root pointer, right? Now after this, for if we reach at the leaf, in other words, we are updating this index to val, right? So whenever we reach at the leaf, it means this is the first node that we need to update, right? Previously, let's say you are updating the 1 to 5, so you are updating the first position to the value 5. So this is the first position will be updated. So what you will do, you will simply return a new node whose left and right would be null, right? So this is a new node whose left and right would be null, and the value of this node would be the given value, right? Now if it is not a leaf node, you will have two children, left and right, right? Now only one of these children will be modified, because you are updating a particular index. Only one of these children will be modified. Either left child will be modified or right child will be modified, depending on where the index lies. So in this case, index lies in the left side, so left child would be modified, right? And right child would stay as it is. So notice that if it is a non-leaf node, you have to create a new node or new root here, because this value will be updated for sure, right? Again, this thing we have discussed multiple times. Basically anything in this path will be updated. So we just create a new node here. We created a new node. Now this node denotes the value at the range L to R, right? Now to fill this value, you actually need the value at the lower indexes first. So you just you want to compute the value at lower indexes. Now if your index lies in the left, this is the case. If your index lies in the left, in this case you will simply update your left child with the basically you have to call the same function again with the left child pointer. This will be saying that what is the previous value here, or what is the previous left child. Now why you need this? Because once you go down from this particular node, you will only be going down in one direction. So you will not go in both the direction, you will only go down in one direction. In this case, you will be going down in this direction, in the right child. So left child would stay as it is, right? So that's why you need the pointer of previous node as well, so that you can point the left child of current node to that new node pointer, to that previous node's left pointer itself. So we just pass in the root node of the previous left child, and it will be m, L comma m. And similarly, if the index we are trying to update is on the right side, we will simply pass on the pointer of the right to the further recursion function. So once you have populated the left or the right, you will simply maintain the other node as it is. So basically, when we are creating a new node from this previous root, we are copying the left and right child as it is. So basically we are saying that, let's say we are creating this or we want to build a segment tree for updating 1 to 5. This is what we need to build, right? Now we know that we'll start from the root. Root denotes 0, 7, so this will be updated for sure. Now one of the left or the right child will be updated. So what you will do, you will simply point the new node left and right to the existing node left and right. Now you decide which one will be updated. You know that in this case one lies in the left, so left will be updated. So you will keep the right child as it is and point your left child to a new node, and for the new node you will just simply call the same function again, but this time for this particular root, right? Previously you are trying to build a segment tree for this entire 0 to 7. Now you are trying to build segment tree for 0 to 3 in the exact same manner. So again you will create a new node, you will point the new node to both left to the previous nodes left and right, and now you will see which one will be updated. You know that in this case the left one will be updated because one lies in the left, so you will simply replace the left pointer to a new node and pass it around. So you will keep on doing this, and finally you will have your new segment tree populated with this particular root node, right? So hope this entire thing makes sense. Again, this entire thing would take order log n extra time complexity and order log n extra space per update. So with that we will stop for now here, but in the next video we'll look at how to actually implement this entire persistent segment tree from scratch. So I would strongly, the motive of not showing the code in this video is to let you try this persistent segment tree by yourself. So you can try solving the same set of problems that we have solved in solved using merge sort trees. For example, we have solved k query, maximum sum queries, giveaway, mkth num. So all of these will be solvable by using persistent segment tree as well, except giveaway. So this is a very important problem to actually understand the difference between persistent segment trees and merge sort trees, or rather it is not always possible to solve all the problems of merge sort tree with persistent segment tree. So you can't say that I will learn persistent segment trees and I will done with it. So you can't say that. So persistent segment tree, there are some problems which will not be able to solve using persistent segment trees, but that will be solvable using merge sort tree, and giveaway is a very nice example of such problem. So just to give you a glimpse, the main reason why, or the main difference between persistent segment tree and merge sort tree lies in the fact that both are kind of storing the state, like both are storing what existed before, right? But in this case you have liberty to update any position at any given point in time, right? You can say, okay, I will update 2 to 4, or basically this particular position to 4, and you can just propagate the update in the chain, right? But if you update this 2 to 4, now whatever next segment tree you will build, this segment tree will be on top of this particular segment tree, right? But if you don't want your next segment tree to be on top of this will not, like, this strategy will actually not work. So in other words, persistent segment tree, if you look at it, is very similar to how prefix sum works, right? So basically you build a segment tree for, let's say, 0 to L, you build a segment tree for 0 to 2, 0 to 3, 0 to 4, and so on and so forth. Now once you have built this entire segment tree from 0 to n, now someone says you, okay, update the ith index again. Now if you update the ith index, you will be creating a new segment tree starting from the segment tree of 0 to I minus 1, right? And once you update the ith index, you will be creating a new branch from here, right? And that new branch, you have to compute everything again after I. So that's like one drawback of persistent segment tree. Basically you can't undo what you have already done. If you are undoing what you have already done, you will be creating a new branch out of it, and whatever you have done after that will be kind of lost, right? So we'll cover this idea again in much better detail in the next couple of videos. For now, as an exercise, what you should do is you should actually try implementing the regular segment tree, not the persistent one, regular segment tree using pointers, and try to get one of the solutions or any one of these problems submitted using the regular segment tree and pointers. And once you are able to achieve it, the next task that you should do is just try solving k query using persistent segment trees. And as I discussed already, the solution would be very similar to how we have solved d query before, or I think enemies is weak before, in one of the previous video. I will link all the videos in the description below or somewhere in the top right section, so you can check them out if you have forget about that. So that's it for this video. If you like the video, give it a thumbs up and do subscribe if you haven't already. Do share with your friends so that they can also get benefited and learn something new from the videos. And I will see you in the next one. Thank you.